Okay, so we're going to continue our discussion about time value of money. Right? This is the second part of the lecture. We had several examples, so it took us a long time, and I'm showing you how to work the calculator as well. So I noticed that our last lecture was almost 75 minutes long, but and this is going to be not as long, but it's still take us some time. But remember, with these lecture videos, you have the ability to pause and rewind and fast forward and play, and so you don't have to watch everything at one time, right? And of course, you can go back and rewatch things that you need to rewatch. Anyways, so let's start with we've been talking about annuities, and the last problem we did in part one had uh, a comparison of two car loan payments, right? But a car payment is like just like a home mortgage payment. It's considered an annuity because it fits the definition, right? The definition of an annuity is that it's the same amount. It the payment is the same amount. It occurs at equal interval of time. So every month, for instance, is and it lasts for a finite period of time, right? And then there's another kind of uh, annuity that does not end. It doesn't last for a finite period of time. It's an infinite annuity, which we call a perpetual annuity or a perpetuity. And we look at that too. And so, as a matter of fact, it turns out that the present value for perpetuity is really easy to calculate. But going back to annuity, uh, typically in an annuity, we actually have payments that occur at the end of each period. Um, and if payments occur at the beginning of each period, then um, it becomes an annuity due, right? So annuity due, not an ordinary annuity, screams bon bon bunny. What is the difference between the two? Explain how the present value and the future value of a 5-year, $1,000 annual payment annuity will be different if we are talking about an annuity due rather than an ordinary annuity. Right? For calculations, assume that the appropriate interest rate is 10%. So first let us examine how the timings will be for this. Okay, so we see that with an ordinary annuity, it's a 5-year annuity with annual payments, and the timing of cash flow is going to be at the end of each period. So in a timeline like this, we start with now, which is representing the point in time now, and then a year from now, that's 1. So that distance between 0 and 1 is the first year, and then the second year, end of year 2, and so on. And the payments will occur at the end of each year in an ordinary annuity, or if it's a monthly payment scheme, at the end of each month, right? But with an annuity due, the payments occur at the beginning of each period. So whether we're talking about present value or future value, we actually, and with future values, suppose the future value of an annuity due will be calculated at the end of 5-year period, just like with an ordinary annuity. And what we will see is that that each payment gets compounded, earns interest for an extra period of time, right? The first one earns interest for 5 years. The second one earns interest for 4. The third for 3 years, right? And the third payment is actually happening at the end of year 2 or the beginning of year 3. Whereas with the regular annuity, in the future value calculation, each payment actually earn interest for 1 less year compared to an annuity due. And you can see that because the first payment, end of year 1, only earns interest for 4 years, second payment for 3 years, and so on. And the last payment doesn't earn any interest at all. So the future value of an annuity due is going to be larger by one interest payment for each of the payments, right? And it's going to be the same for present value, because in present value calculations, we don't compound, but we discount, right? So we are going to have one less period of discounting for an annuity due, and the present value of an annuity due will also be larger by one interest payment for each payment. So the present value of an annuity due is larger due to discounting of each payment for one less period. Similarly, future value of an annuity due is also larger due to compounding of each payment over an extra period. And so the present value of an annuity due is the present value of a regular annuity times 1 plus I. Likewise, the future value of an annuity due is the future value of a regular annuity times 1 plus I, right? And of course, financial calculators have and spreadsheets, they have settings that allow you to change the payment mode from end of period to beginning of period. So you could use those, change the payment mode, and then you could calculate present values, future values. But just for present value or future value of an annuity due calculation, you can simply take a future value of regular annuity and multiply it with 1 plus I. Okay? So for a 5-year annuity, basically present value of a regular annuity would be 1,000 times the factor, the present value of interest factor, and that'll give us 3,790.79. You take that 3,790.79, multiply it with 1 plus the interest rate, and you get 4,169.87, right? That's the present value of annuity due. If this 5-year annuity was at the beginning of each period. Future value, we can use the future value factor to calculate the future value of a regular annuity, 6105.10, and future value of annuity due is 6105.1, which is the future value of regular annuity times 1.1, or 6715.61, right? So I'm going to, let me stop the slides right here. Let's look at the calculator here. And you could simply use the calculator functions and say for a regular annuity, if 1,000 is present value, right? Do second if we declare the TVM worksheet, then sorry, 1,000 is payment, and we're talking about a 5-year annuity. So 5 is N, and interest rate is 10%. 10 is I by Y. Then if we compute future value, we get this 6105.10, right? And that's the future value. If we compute present value, we get, I think I needed to clear the future value over here because it's messing up. Let's recalculate the present value. We do 1,000 as payment, 5 as N, 10 as I by Y, compute PV, and we get 3790.79, right? So that's the present value for regular annuity. We multiply it with 1.1, 1 plus the interest rate, and we are going to get 4169.87, right? And that's the present value of annuity due. Or, so that's one way of getting it. Or you can say, in the calculator, you can say, change the mode, and second PMT brings us to the BGN key, and it shows us right now the calculator is set to assume all payments occurring at the end of each period. we can change that by using second and enter, which is a set key. And now it's, you can see the screen says BGN. Then you do second compute to quit, get out of there. And now if we calculate, say the present value of, let's say 1,000 is payment, 5 is N, 10 is I by Y, and then compute PV, I get 4169.87, right? So that's the present value of annuity due. Then if I want, I need to go back and second clear FV to clear TVM, and it's still in the begin mode. You can see up on top screen it shows that it's in the begin mode, and we're going to say 1,000 is payment, 5 is N, 10 is I by Y, compute FV. Right now we have a future value for annuity due, which would be 6715.61, 671.5.61. Okay, so by changing to begin mode, we're able to evaluate annuity dues, right? But if it's a simple problem and there's not many complications, like you get, suppose you have to find the payment on an annuity due, then it might help you to change the mode and do this. But just to get the future value of annuity due, well, we can simply add a step. We just calculate future value of a regular annuity and then multiply it with 1.1, right? And you get the answer. And the reason I prefer doing it that way is because then I don't have to remember to change this mode back, because most of the problems we'll be doing here will be using the end mode. So before I move on, let me change it. Second and PMT, second, enter. So now we changed it from begin to end, then second compute, so we are out of that. And now the BGN on top here is gone. So I know it's back to the default mode of end of period payments. Okay. All right. So let's look at this. The title here says complex problem with annuity due, right? What makes it complex is simply that there are multiple steps involved. So first, Ellie Mae, who is 25 now, would like to quit her job when she's 35 and travel the world with a gypsy caravan. In order to realize this dream, she would like to be able to draw $50,000 at the beginning of each year from the time she turns 35. Actuarial estimates put her life expectancy at 85. Uncle Jed has just bequeathed $200,000 to her. Ellie Mae wonders how much more she needs to save each year between now and until she is 35 in order to realize her goal. Assume that she can invest her assets 10% per year. All right, so basically, we see that Ellie Mae it's got 10 years, right? So she's 25 now, and she wants to quit her job at 35 and travel the world with gypsy caravan, which means she's going to need $50,000 per year, which she will need to withdraw $50,000 per year at the beginning of each year from the time she turns 35, and then she's expected to live till 85. She's planning for 50 years of being able to withdraw $50,000 per year, right? She's got $200,000 right now, yeah, right? So what she wants to know is how much does she need to save every year? for the next 10 years, right? She's 25 now, and so every year until she's 35, in order to realize her goal. Assume that she can invest her assets at 10% per year. So this is a multiple part problem, and the timelines are very useful here. So what we're going to need to do is draw a timeline, basically from 10 years from now, when time she's 35 till the time she's 85. But since we're talking about payments at the beginning of each year, right? The timeline doesn't stretch to 60 because the last payment is going to be at 59. This is an annuity due, right? The payment's occurring at the beginning of each year, so she needs to withdraw. So including 10 to 59, that's 50 payments of 50,000 each. So what we need to find out is how much does she need to deposit for each of the next 10 years in order to be able to do that, right? And so to find the answer, we're going to first need to calculate the present value. Now, what would she need to have in the account after 10 years? That's the present value of a 50-year annuity with payments occurring at the beginning of each year. So it's a 50-year annuity due, right? And we need to find the present value of that annuity due. Then we're going to take this amount and say, well, that's what she needs to have 10 years from now. So we'll take that amount, make it a future value, and calculate how much all of that comes out to in today's dollars. We'll want to find out the present value of that 10 years ahead. And so if that happens to be 200,000 or less, then we're good. If not, whatever the excess is will become a present value of an annuity, which she needs to save every year, like, right? It's an annuity, and she has to make payments every year for the next 10 years. So, and we have the present value of that amount, so we'll have to find the payment on those. And that is going to give us the answer, right? So that's the scheme. The scheme, it is a multiple step problem, and if we draw out a legitimate scheme, we'd be able to find the answer, right? Let's use our calculator. Let's use our calculator to get this problem, right? Because there are several problems and several steps to it, and let's use our calculator and let's look at the scheme. We get 50,000 per year. I'm going to say second, clear TBM, 50,000 per year, 50. Let's just leave everything in thousands. We'll say the answer comes out to be 1,000, right? Second FV. 50 is the payment on a 50-year annuity, so 50 is N, and it is, the interest rate is 10%, so 10 is I by Y, and we compute payment. Oh, I messed up actually. 50 was the payment, and we needed to compute present value, right? And so this is the present value, but it is a present value for regular annuity. What we have instead, we need is a present value of annuity due. So we'll multiply it with 1 plus the interest rate of 1.1, and gives me 545.3147, whatever it is. It's in thousands of dollars, but that is what I'm going to need. So make that the future value, right? So let me make this the future, but let me first save it. Save this value, store 1, then second FV. Well, I stored it to be safe, but that number remains on the screen. So let's just make it the future value. I want to find out what it is worth in today's terms. So it's 10 is N, right? 10 years ahead. I'm going to find what the present value is 10 years back. 10 is N, 10 is I by Y. Compute PV. And it turns out to 210,242, right? Now, she has 200,000 in deposit, to deposit, which is her inheritance, right? So she's got the 200 to deposit, but she needs 210 plus thousand. So there is a difference that needs to be made up, right? And that difference is the 210.242 whatever minus 200. That's 10.242. Let's store this number, although we may not need to. And then second FV to clear TVM. That 10.242 in thousands is the present value of an annuity. So that's the present value of an annuity. Make that present value. And we want to find out what the payments are. Now this is a regular annuity. It's not an annuity due. So it's just a regular annuity. Let's find out what the payments are going to be for 10 years. 10 is N, and 10 is I by Y. Then compute payment, and we get 666.91, basically $1,667, right? In dollars, or $1,666.91. So that's how we get the answer. Of course, that's what we have shown to us. Well, I'm going to cycle through all this, but the process is explained in the next couple of slides. And this is our answer, right? Which we got. So 1,666.91. That's the annual payment she needs to make into her account over the next 10 years in order to accomplish her goal. Okay, let's look at how these payments are structured. Each payment in an annuity actually contains a little bit of interest and some of the original amount or principal of the loan that's being paid back. So let's look at a simple 5-year annual payment annuity here in this example. 50 Cent and a Euro is a hip-hop band that needs $100,000 to finish cutting up their latest album. They approach Habibie of National Bank, which has agreed to provide them a loan which must be repaid over the next 5 years in equal annual installments payable at the end of each year. The stated interest on the loan is 10%. How much will their annual payment be? Build an amortization schedule to show the principal and interest component of each loan payment. Okay, so what is an amortization schedule? It basically is a schedule that breaks down the payments in an annuity to its interest and principal repayments, and clearly displays how the loan is paid. So we can go and basically first let's find out what the payment on the loan is going to be. The second, if we clear TVM, right, we got we had $100,000 that is the loan amount. So $100,000, that is the present value. I want, you know what, I want the payment to come out as positive, so I'll make this negative. Negative is 100,000 is present value, and then 10 is I by Y, and 5 is the number of payments, right? Then compute payment, and the annual payment is 26,379.748 or 0.75. Okay. Now, so this is how the loan gets repaid over the first 5 years, right? Over 5 years. So end of each year for 5 years, you're going to pay 26,379.75 to repay the loan amount, right? So that was the answer we just got. That was right. the payment. Let me make sure. Yeah, it is 26,379. Okay, so that was the answer we had. That's the loan payment, and the payment remains the same each year. But as time goes by, we are paying off some of the loan, and the loan balance will decline until it becomes zero by the end of the loan term, 5 years in this case, right? So we're paying off principal and interest. What's the interest do? Well, it's 10%, right? So after the first year, 10% of $100,000, the original amount of the loan, is $10,000. So, but our payment is $26,379, right? So $10,000 is interest, and the remaining is going to be principal amount that we pay back, amount of the loan, or the $100,000 that we pay back. So the remaining from 26,000 to 10,000, remaining is 16,000 plus is the principal that's repaid, right? So after 1 year, we don't owe $100,000 anymore because 16,379 of the principal has been repaid. So subtract that and you get 83,620.25, and that is what we owe after 2 years. So at after 2 years, the interest will be not calculated on the original 100,000, but only this reduced principal value of 83,620, right? It is still 10%, so 10% of 83,620 is 8,362.03. Of course, we're rounding up, rounding numbers at this point, but 8,362.03. But we are paying the loan in equal annual payments of 26,379, right? So the principal repaid now after the 2nd year's period payment is the interest of 8,362 subtracted from the annual payment of 26,379 to get 18,017.72, right? So you start to see how this is working out, right? And here's the entire 5 years schedule. We start with 100,000 in loan after the first year, after we made the annual payment of 26,379.75. That remains the same every year, right? It's an annuity payment. Interest for the first year is 10,000, which was 10% of 100,000. We subtract 10,000 from 26,379, we get 16,379.75. That's the principal repaid. So take that off the original principal balance, and we get 83,620.25. And now that becomes our starting point in year 2, right? Once again, the annual payment will not change, right? But the interest that's due will change because it's only 10% of the remaining balance, meaning more of the principal gets repaid up on the 2nd year, leaving us with an ending balance of 65,602.53, right? And that is 83,620.25 minus 18,017.72 will give us 65,602.53, which will be our starting point for 3rd year and so on. And because the principal on the loan goes down every year, the interest that we pay, the 10% on that balance, also goes down every year. The interest goes down every year. As a consequence, the amount of the loan we pay each subsequent year is higher. until at the end of year 5, we have zero balance. We've paid off the entire loan. And that's the amortization schedule. It shows up as exactly where the money goes, right? Now, once you have calculated the payment on a loan, and it's very important to note that once you have calculated the payment on a loan, you can actually see these lines, like line 1, line 2, line 3 of the amortization schedule. You can see this in your calculator. But you can only, see one number at a time. So let's look at, and that will be the AMORT amortization, which is the second, and is a second key. Second PV gives us, so first it asks for two things, right? What's the P1? And because it's looking for a line, it has the capability of adding up. So suppose you wanted to add line 1, 2, 3, then you could say P1 is 1 and P2 is 3. But if you just want to look at one line at a time, then say P1 is 1, enter, and P2 is also 1, enter. And now we're looking at the first line in the schedule. So balance after first payment, 83,620.25, right? That's what you're looking at in the calculator. Down arrow, principal, that's repaid, 379.75. Then interest, of course, interest was 10,000 that first year. Right? Now, if I want to look at the second row, P1 equals 2, enter, and P2 equals 2, enter, right? Because I'm only looking at row 2. Now, if I do this, I get the balance of 65,602.53, principal 1817.72, that's the principal repaid, interest 8362.03, right? Now suppose I wanted to sum up the first 2 years. Like I want to see, what's the balance after 2 years, but how much principal is being repaid after 2 years. So I'm going to be adding these two numbers. How much interest is paid at first 2 years, I'll be adding these two numbers. Then what I'll do is make P1 equal 1. P1 1, enter, arrow down, P2 equals 2, enter. Now I'm aggregating the first two rows, and now you'll see that the balance, of course the balance is at the end of year 2, whatever the balance is. When we look at principal repaid, that's actually the sum of 16,379.75 and 18,017.72. That's the sum of these two numbers of the first two columns in principal repaid. Then if I go down, interest. The first year was 10,000. The second year it was 8,362, and we're just adding those two, and we're aggregating 2 years of interest, right? So that's what the P1 and P2 are for. If P1 and P2 are the same, then you're looking at one row. If you get P1 and P2 are different numbers, then they're summing up. Say if I want to see what happens in the last 2 years of the 5-year, then you can just say P1 equals 4, enter, and P2 equals 5, enter, and it'll show us what's going to happen. At the balance at the end of year 5 is almost zeroed out, right? Because it paid off the loan. The principal that's repaid in the last 2 years is 45,783. So almost 46% of the loan gets paid back in the last 2 years. The interest is only 6,967 over the last 2 years, and so on. So that amortization button can show you these numbers from the schedule, albeit it can only show you one number at a time, right? Because of the screen and the calculator. Okay, and now let's move on to a perpetuity, right? So you won the grand prize in Mardi Gras Lotto. The prize comes in the form of 10 bead necklaces worth $10 each, payable every year throughout eternity. If the applicable interest rate is 5%, how much is the prize worth to you today in monetary terms? Well, so what we have is a lotto that pays you 10 necklaces worth $10 each, so say $100 every year throughout eternity, like forever, right? So how much is this prize worth to you today if interest rates stay 5% per year forever, right? And surprisingly enough, the answer to this is very, very simple. And you can think about it this way. What would it take for you to create $100 payment that lasts forever if you can get 5% interest, right? Well, so what is $100 on your 5%? You need to find an amount, and when you calculate 5% of it, you get $100, right? And how can you do that? Just take 100 and divide it by 0.05. And what that means is that you get $2,000. And $2,000, 5% of $2,000 is $100, right? You put $2,000 in the bank and you get 5% interest. After a year, you have $2,100 in the bank, right? And you withdraw the 100, leave the 2,000, and a year later you have 2,100 again because of interest. Withdraw the 100, leave the 2,000, and as long as interest rate is 5%, you can keep on doing that forever, right? We call this kind of annuity a perpetuity, right? It's a perpetual annuity. So we got $100 payment forever. The present value of perpetuity is really that simple. As we had done, I took the 100 divided by the 0.05 interest rate to get 2,000. That's the present value for perpetuity. So take the payment divided by the interest rate and you get the present value of perpetuity. It's simple as that. And so this prize is actually worth $2,000. Okay, let's look at some comparisons. You intend to be a lifetime subscriber to Bean Counters Quarterly. You can obtain an annual subscription for $12 or a lifetime subscription of $115, right? If you expect long-term interest rates to be 10%, which is a better option? What projected long-term interest rate will make you indifferent between the two choices? Okay, so you can pay $115 right now, or you can pay $12 per year forever. We're going to treat a lifetime subscription like it's a perpetuity, right? So we can assume that it's equivalent to a perpetual subscription because there's not much difference between, say, a perpetuity and a 50 or 100-year annuity, right? And so we can make that assumption that the $12 lifetime subscription is a perpetuity, right? And this assumption is appropriate because present value of very distant payments add little to the value of a stream of payments, and that's especially if interest rates are not too high. For instance, not too low. Now, for example, $12 to be paid 100 years from now, discounted at 10% per annum, yields a present value of less than 9/100th of a cent. As a matter of fact, we can figure this out. I said second compute in the calculator to get out of the amortization mode we were in. Second clear TVM. Let's say $12 is future value, 100 is present value. Oops, messed that up. Let's clear this again. $12 is future value, 100 is N, and 10 is I by Y, and let's say, and then we want to find out how much that's worth today. Compute present value, and you get 0.00087, right? So it's less than 9/100th of a cent. Right? All right, so basically we're saying here that it's appropriate to consider a lifetime subscription to be equivalent to a perpetuity. In which case, we can simply find out that the perpetuity, the present value of the $12 per year forever, perpetuity of the $12 is payment, right? The $12 payment in perpetuity, the present value of that perpetuity at 10% interest rate is payment by the interest rate, or 12 by 0.1, or $120, right? The perpetual subscription costs at $115, right? Or which is the lifetime subscription costs us $115. So it is cheaper to just buy the lifetime subscription, right? Now, the other part of the question was asking us, at what interest rate are we going to be indifferent between the two options? Which means that we got to find an interest rate at which this present value of the perpetuity of $12 annual payment will exactly equal $115. Or we're not talking about 10% interest rate anymore. We're talking about an interest rate which makes us indifferent, an unknown interest rate. Or $12 by I equals $115. When we solve for I, we get 10.43%. So if interest rates were higher than they are now, 10.43 or higher, then at 10.43 will be indifferent, but higher than 10.43, say the interest rate was 11%, then we're going to say the annual payment option is better. Well, we'd looked at calculating effective rates previously in part 1 of time value of money lectures. Here's another example, and it kind of exaggerates it to see in extreme circumstances the difference between effective rates and nominal rates can be quite stark. So let's look at this. Sharky, the loan shark, extends you a loan with the stipulation that you pay back double the amount at the end of the month, and the pain of a busted kneecap, of course. What is the annual percentage rate on this loan, and what's the effective annual rate? All right, so we're going to set aside the cost of fixing a busted kneecap, medical expenses, the pain, etc. But just let's look at these numbers. If you have to pay back twice the amount, that means the interest rate is 100%, right? And you have to pay back twice the amount at the end of the month. So we're talking about a monthly interest rate of 100%, right? Which means that the nominal rate, which is the quoted rate, which only needs to be a nominal rate, we also call it APR, annual percentage rate. The nominal rate is the periodic rate of 100% times the number of periods. So this is a monthly rate. So I'll just need to multiply this with the number of periods in a year. There'd be 12 months in a year, right? So the nominal rate is only, 12 times 100 is 1,200%, right? But the effective rate is the real cost of the loan, because 1,200% would be the interest rate if you only had to pay back, say after a year, you had to pay back 12 times the original amount, right? So if you borrowed $100 today and waited a year, then you would have to pay back $1,200, right? And then your interest rate is 12%. Sorry, 1,200%. Let me restate that. You would pay back the original 100 plus $1,200, so a total of $1,300, right? And then your interest rate would be 1,200%. But that's not exactly how this is working, because after a month, if you don't pay your $100 back, then you owe Sharky $200, and you got to pay 100% interest on that. So after 2 months, you got to pay $400 back. If you don't, then after 3 months, you have the 400 becomes your principal, and another 400 that you have to pay. You got to double that. So after 3 months, it's $800. After 4 months, you're at $1,600. After 5 months, it's $3,200. And you can see how this is starting to get out of control, right? We got to calculate the effective annual rate, and the way it was defined earlier, this effective annual rate is 1 plus the periodic rate, in this case the monthly rate, times the number of periods in the month, which is in this case 12, that's number of months in a year, right, minus 1. And so in decimals, the interest rate, 100% is just 1, right? 100% is 1. So we have to do 1 plus 1 raised to the power 12 minus 1. And when you crunch this out, I'm not going to take you to show how to do this in the calculator. I mean, you know, this is simply 2 and then y to the power x, and 12 equals, and then minus 1. It's going to give you 4095. Now this is the answer in decimals, right? In percentages, you add 2 more zeros to it, and it's 409,500%. Right, so it's hardly 1,200%, which was the APR. Effectively, this amounts to 409,500%, and such is the power of compounding. And it's so startling because the interest rate is so high. It's 100% per month. Okay, let's see if you could figure out if something sounds right. You know, this is title spotting a bad deal, and let's see if we can spot a bad deal in here. So Brittany Haley held a bid and demanded an explanation for the following advertisement. In her opinion, the advertised deal does not appear right, and the implicit interest rate is not 0%. Do you agree? Right? And so what we're looking at here is an advertisement. Says closeout furniture going out for business sale. Oak executive bedroom set, only $600, 0% interest, payable in 12 monthly installments of $50 each, or pay cash, $550. Right? So you have 12 monthly installments of $50 each, and so if you 50 times 12. It's 600, and the bedroom set is or 600, they say. So it's 0% interest, right? So does this look like an honest deal? Well, given the title of the slide, you know what I'm going to say. It's not. You can tell that. How can you say that? Well, the reality is the bedroom set is not worth $600. Why? Because you can pay cash. You can pay $550 right now and take that bedroom set home. So it's not worth $600. It's worth what you can take it home for right now. So it's only worth $550, right? So you can either pay $550 right now, or you make 12 monthly installments of $50 each. And obviously, since the 12 times 50 is 600, you are going to pay some interest. You're paying some interest on this deal, right? And I could also tell that this is a bad deal because of how they're trying to dupe us by saying going out for business sale, right? So this is not, they're not going out of business, they're going out for your business. So just paying attention can make you aware. But let's figure out what is the interest rate on this deal, right? Basically, it's not going to be that hard once you realize that $550 is the present value of 12 monthly payments of $50 each, right? So something that's worth $550, if you are going to take it on installments, then it's going to be $50. So I did second FV, then 50 is PMT, and there are 12 of those payments. 12 is N, right? So you got to make those payments on $550 that you borrow today, right? So you got to make this negative, or you can make the $50 payment negative and $550 positive. But in our but I had already put $50 as positive payment, and so $550 negative is the present value, right? And before I proceed, so what is the idea here? Well, remember that if you take this bedroom set home and make those $50 payments, instead of paying the $550, you pay 12 monthly installments of $50, right? So taking the bedroom set home, which is worth $550, means you get something worth $550 now, and you have to pay $50 every month for the next 12 months. So from your perspective, the $50 would be cash outflow, negative cash flow, and $550 will be positive because you're taking this bedroom set home. It's a positive cash flow, right? Okay, so that's one way to get the sign straight. But remember, whatever you're doing, it's the opposite for the seller. So the seller is out $550 when he lets you take the bedroom set home. So from the seller's perspective, I can say present value is minus $550, and then over the next 12 months, they get $50 each. The payment will be positive $50, right? So the signs I put in the calculator are consistent with the seller's perspective. But you just have to be consistent in the sense that you take one party's perspective while determining the sign of cash flows, and then you get the right answers, right? So once again, here I've got present value of $550 and future value of $50, payment of $50 and 12 as N, and then I compute I by Y, and I get 1.3647, right? Now what is this? This is actually the monthly rate. That's the monthly rate, right? And so that's the monthly rate because it's a monthly annuity, right? And that's what we got. That's the monthly annuity. If you multiply it with 12, you get the nominal rate, the quoted rate, which by law, the advertiser should have told you that the interest rate should be 16.38% at least. But most banks actually tell you what the effective rate is. And to calculate the effective rate, we do 1 plus the interest rate in decimals. So 1.3647 is 0.013647, right? Raised to the power of 12, there's 12 months in a year, minus 1 will give us 0.1766 or 17.66% if the effective rate. So it's hardly a rate of 0%, right? It is well, they're trying to prey on people's lack of financial awareness and such deals. Well, this is going to be the end of our time value of money lectures. I hope you learned a lot in this chapter. You actually get to learn skills that you're going to be applying in real life.